composite material, and in particular here you can see a cross section of the beam. They still have the line of the plane of the symmetry, but they come up with two different materials. And if we want to continuously apply the formula of the symmetric bending to these problems, we have to modify the problem statement in particular for this kind of things. And the concept is pretty straightforward. And again, our problem is this ny over I minus sigma. This is the bending stress using the symmetric bending. On the composite, you can see there's a discontinuity, there's a connection, there's here the interface, the stress at the interface is not continuous. And in our problem of O1, if you remember, this is for example, this is the neutral axis, and then this is the beam, okay, portion of the beam. So the bending is like this, and for this case, we know that the stress, distribution of the stress must be like this, continuous. So our job to deal with this problem is to try to reshape the distribution of the stress to make the stress distribution continuous by doing something. Okay, otherwise we wouldn't be able to utilize that equation. And the strategy is this. You can see, using this as an illustration, the stress at the lower portion in material 2 seems is a certain number of the fold larger than the other one. Right? So that means you can simply compare the stress at the interface here. The stress in material 2, for example, here, for example, 3 times larger than the stress in material 1. If we want to stretch and to make the stress equal, then strategy we can do is this. We know that the stress is about the force, stress is the force divided by the area. If we want to get the stress here, the continuous, for example, if we want to get the 3 times larger stress back to the 1-time portion, the only way we can try is to imagine that the cross-section on material 2 increases by 3 times. In this way, we'll be able to dilute in concept the stress and then make the things continuous. Okay, so that is the principle. And so that means into here. So if we try to get they call the transformed cross-section, for this example, the transformed cross-section is try to increase, imaginary, increase the lower portion by 3 times. Again, the 3, how to get the 3? That is the portion measured from here to here, okay? And then based upon this one, you can see basically we rescale, we scale down the stress distribution in the lower portion, and then you can see the whole thing become continuous. Then we can apply this formula. This formula applied to here. This is corresponding to the transformed cross-section. Everything based upon applying that formula on the transformed cross-section. Once we've done the calculation, then one more step is we try to interpret the result back to the real non-imaginary portion. Yes?
When you make your transformation, the neutral axis stays in the same spot?
Say that again.
When you transform one material, the neutral axis doesn't move?
No. The neutral axis won't move. Yeah, won't move. Okay. And the transformed cross-section is to increase or decrease the dimension that is parallel to the neutral axis. Okay, you only have one option in 2D. Okay, and so that is the concept. And so those are the details. And if you can comprehend the concept, you don't have to look at the details here. And in particular, in this page, I summarize the steps. Okay, so how to the whole thing basically summarized here. And probably we can try is this. Here I can give a very quick summary. Basically here is this. We decide we want to transform the information on the lower portion. And in your calculation, you can decide either way. Okay, you can decide to transform the upper portion. Okay, In this way, you can try to enlarge the stress by stretching to that direction. If you want to imagine enlarge the stress there, then likely is you have to decrease the area in the way to exchange for the stress increasement. But either way, that is equivalent to saying is this: you pick one material. Here is the composite, but you pick any one as your reference, and then you calculate how much is the ratio here, and we call N. The ratio basically is equal to taking the ratio of, for example, here, 1 is the reference material, E2 is the other one. So the ratio of this one, N, simply is E2 divided by E1, and again, E1 is our reference, unchanged. The 2 corresponding is we're going to transform. Okay? So that means the N will give you, for example, that is the number I mentioned, 3, for example. So this N will be the fold, the number of the folds that are going to increase for that portion. So we increase the dimension by n-fold, and that per this formula. So we proceed to the calculation of the stresses on this transformed cross-section. And once we've done the calculations, then we have the stress in here, corresponding to the material 1. We have the stress here corresponding to material 2. But those information are our conceptual, not real model. The one final step is to interpret the result back to here. And that interpretation is this one. I didn't write it down. That's okay. Probably you can write it down. Is this. Once we have all the calculations, then to interpret the result back to here is this. For whatever the stress you calculated in this portion, you multiply by n. That's the stress corresponding to here. Because you calculated the stress in here, that is n times smaller than this one. That is the real one. Got it? So that's kind of procedure. And we can take a look at 1 or 2 examples and then to polish this